southeastern Indiana County. It's located right along the Conemaugh River, which makes up the southern boundary of Indiana County. I'm sorry, I'm just getting things situated here. There we go. West Wheatfield Township is about 31 square miles in size, and it's located between Blacklick Creek to the north and the Conemaugh River to the south, and between Chestnut Ridge to the west and Laurel Ridge to the east. The major town in the township is Robinson. There are some other towns which I think would probably better be classified as ghost towns: Climax, India, Germany, Heshbon. They all have a few houses left, but not a whole lot is remaining in their community. And actually, there is a trail that comes along Blacklick Creek to the north here that's called the Ghost Town Trail. There's also a large state game lands. 153 is located in the southwest corner of the township. So like I said before, the biggest town is Robinson. It's located right on the Conemaugh River, and it's located next to Pack Saddle Gap, which is the gorge that cuts through Chestnut Ridge. And it was once a prosperous town with quite a few different mines and brick plants. Most of the industry is closed down at this point, and along with that, the jobs. And as a result, the area has a high poverty rate, and the township supervisors are hoping that increasing the recreational opportunities of the area will also mean more job opportunities for the local residents. So after my initial meeting with the township supervisors, they gave me a quick tour of the area. To the east of Robinson, this is the edge of the town of Robinson right here, there is a large active treatment plant that's treating discharge from a very large coal mine. It's the responsibility of the mining company to keep the water treated. So that's not of concern during this assessment. There's also a very large coal refuse pile that's nicely eroding into the Conemaugh River, and you can also see this plume of orange here. And at first I thought, boy, that active treatment plant is not really doing well treating the water, but it's actually from an abandoned source way up the stream here. This is Richard's Run. So here's some pictures of the streams that flow through the town. This is Richard's Run, where that mine drainage is coming down and joining the Conemaugh here. And then this is an unnamed tributary that's even worse quality. And you can see this is right in people's backyards. So as I started to do my research, I discovered that the township has been very heavily mined. I found this map of Indiana County that is fairly comprehensive and shows the number of, or the amount of mining, the underground mining in the area. And I counted a total of 17 different underground mines in the township. And some of these were really large mines, because right here in the corner, there's actually a power plant. And so these mines would just, they basically come out of the hillside and feed the power plant. In addition to the underground mining, there is about 7.6 square miles of surface mining that went on, and there's a total of 42 different surface mines. So just eyeballing it, I'd say about 3/4 of the township has been mined. So there hasn't been a whole lot of restoration work that was done in this area in the past. And one of the main reasons, I think, was because of the polluted condition of the Conemaugh River and Blacklick Creek. This is a map of the Kiski-Conemaugh River Basin from 1999. It shows AMD affected streams as being red, and the area that we're interested in is right in the center of it. So this has actually changed. The water quality of the Conemaugh River has improved quite a bit in the last 15 years. There's been a lot of passive treatment systems that have been constructed. And I guess most importantly, the St. Michael active treatment plant went online in 2013 on the Little Conemaugh River. And this is a picture of the plant. And prior to treatment, this is what the stream looked like, and this is what it looks like now. So we are getting, some better water quality in the Conemaugh River. So it makes sense to start looking at some of these other areas. These are. So I focus my efforts on the streams that flow into the Conemaugh, because that's what was shown to me. That's what they're most interested in dealing with. And there are three different streams: Richards Run, which is broken up into the West Branch and East Branch, and also Roaring Run, which is on the western side, and a large part of it is state game land. And then this unnamed tributary that comes up the middle. And I'm calling it unnamed tributary E, and I'm naming that after a coal mine permit application that I was able to find. And I guess I really didn't really know what I was getting myself into with working on this project here. So when I begin a new assessment project, I always look for existing data. And this is a map of the surface mines, the historic surface mines in the area. And I look for data from the DEP, watershed organizations. I look at the underground mine maps. I talk to locals, and I found out that this mine right here it was actually still active. This is called the Wheatfield operation, and it was operated by River Hill Coal Company. And I just want to stress that these mine permit applications are excellent sources of information. They actually conduct a very thorough hydrologic analysis of the area in order to get their permits. So not too long ago, to get this permit data, you'd have to go to their office and sort through the permit application and all the subsequent paperwork, and there could be hundreds, if not thousands, of pages of documents that you'd have to go through. And a lot of those permits have been scanned now, and so you just had to give them a call, which is what I did. This permit was issued in 2004, and they did a very thorough hydrologic analysis. And I have never seen a permit application quite like this. But this is all the different sample points that they collected during this study. And there were over 360 sample points, and they were broken down into background sample points, which were 2 samples prior to mining, and they weren't directly associated with the mining. And then monitoring points, which are 6 samples during mining, or I'm sorry, 6 samples prior to mining, and then quarterly thereafter. So one of the things that they want to look for are existing sources of pollution, because they don't want to be held responsible for it. And in Pennsylvania, we have something called Subchapter F points, which is named after the section of the code of regulations, and it allows you to identify existing sources at AMD, so that you're not held responsible later on. So the mining company was originally going to mine this entire area, which would have basically cleaned up everything. There's some alkalinity in the overburden, and it would have neutralized the acid producing materials. And I wouldn't have to be doing anything actually. But unfortunately, they were only able to mine a few small areas. I think there's one area up in here, and then an area over here. And the coal market went sour, and I guess they couldn't make a profit, and so they stopped mining. So now we have we have to deal with all these sources of pollution, but we have lots and lots of data, which is they're probably worth hundreds of thousands of dollars. So I was given some of the more recent data in Excel, but there is also just reams of data that was scanned, and I've had to digitize. So after putting it all together, I created this master table of sample points, and that's how I was able to create the map of all the different sample point locations. So I added details such as the maximum flow rate, the pH, the minimum pH that was in the data set, whether or not it was a subchapter F point, and whether or not it was a stream. So I was able to create this GIS map based on that table, and they had 30 different stream sample points, and then I classified those stream sample points by the pH, which is crude, but gives you an idea of what kind of quality you're going to have in that section of the stream. And you can see upstream, the quality is actually pretty good. Pretty much every upstream point is above a 6. And as you go down into the valley, towards the mouth is where it's picking up a lot of the discharges. So I did the same thing for all the discharges, springs, and wells that were sampled during this study. And so you can see that the eastern side of the permit area seems pretty good. But if you go right down the center part of this valley here and unnamed tributary E, that's the worst part. And I'm beginning to think that they named unnamed tributary E for evil because of just the amount of discharges that are in that valley. And I'd be afraid to just dig a hole, you just have bad water spewing out of it. Like it is really, really bad. So I was able to, with the data that I have, I didn't go through all the historic data that was about 25 years old, but I tried to use the more recent data. I was able to select the top 10 discharges based on loading. So here they are shown on the map. WF 337 was the biggest discharge, and WF 332 was the next biggest. And you can see that the amount of loading in this these two discharges is just incredible. This is kind of off the charts for discharges. Now, this is another way to look at it. I did a top 10, but actually it was a top 11 for the watershed. I kept on WF 111 because when I looked at the older data, it actually would have been one of the top 5 discharges, but the flow rate has gone way down. So I want to definitely look at that when we get to our sampling here. So you can see how bad WF 337 and 332 are in comparison. I definitely do want to do some additional sampling here, verify the flows and the quality. all the water quality, for these permits, they're required to go to certified lab. So I think the water quality is going to be pretty good, but I just definitely want to double check some of the flows. So as far as future work, I want to sort through some of the remaining discharge data. I want to look through and pull out the sites that are over 10 gallons a minute with a pH less than 5. That'll allow me to, I guess, narrow it down to sites that could be potentially bad. And also, I want to do some sampling, because after 25 years, some of those, background samples, if it was, there could be some real changes to the quality of the water, especially if it was related to surface mining. Not so much with underground mining. Those discharges tend to be pretty constant for a very long period of time, even hundreds of years, is what I've heard. But I want to do some sampling here. We're going to look at the upstream and downstream sections of the streams again, and also look at all the top 10 discharges. And I just wanted to leave you here with, this is the WF332. It doesn't look like much. It only flows about 20 gallons a minute. But at times, the water quality has the maximum values that we had for iron was around 2,500 milligrams per liter. Aluminum was 600 milligrams per liter, and the max acidity was 8,500 milligrams per liter. So this is what caused the giant plume in the Conemaugh River here. There really isn't too many other sources on Richards Run. So I think that's about all I have. If you, thank you for listening to what I had to say, and if anyone has any questions, I'm happy to try to answer them.
Thank you so much, Shaun. We do have a couple of questions in the chat. So, how many samples did you take per seep discharge point?
So we actually have not done our sampling yet. I've been sorting through all this data, and it's been taking me longer than I wanted. So we're going to take 2 high flow samples and compare that against the data that we have in this robust database that we have now from all the mine permit data.
Awesome, thank you. Hey, another question. Do you have any thoughts on suitable remediation options? Melissa doesn't recall the mine pool map. Is it possible to pull directly from the mine pool to treat?
I have not gotten to looking at the mine pool. There are some existing mine pools that are being treated by the active treatment plant. I think some of these smaller discharges might be suitable for passive treatment. I think the flows are going to change some in comparison to what they measured. Just looking at the data, I think a lot of the sites actually would probably be suitable for passive treatment.
Perfect. Okay, next question. Were O&M costs considered for the feasibility study?
I think that's going to have to be a next step. We only had a very little bit of funding for this project, and now that we know what's out there, we're definitely going to verify things, but we're going to seek additional funds to put together conceptual designs and consider the O&M costs associated with that.
Perfect. That's all of the questions that we have right now in the chat. Thank you again so much for your presentation, Shaun. And back to Rachel for our next introduction.
Thanks, Shaun. It was really nice to see all of that data. That's a really bad seep. So our next presentation will be a research spotlight from one of our 3RQ university partners, Busler University, and they'll be presenting on carbon breakdown in AMD streams. Katherine Cutlip, a graduate student, will be giving the presentation, but we also have James Wood on the call. So thank you both.
Hi, give me 1 second to just get this into the proper view and then I will share it with you. Because I have to share my screen with you first. Sorry, there's too much stuff and I can't see. Okay. Okay, so I am in my last semester of my graduate program right now, and I have been studying the effects of mine drainage on the local ecosystems here where we live. So the impacts of abandoned mine drainage on freshwater ecosystems. So mine drainage, for anybody who's unfamiliar, is water that is polluted from contact with mining activity and normally associated with coal mining. Obviously, we live in West Virginia, so there's a lot of coal mining around. This particular picture is part of the creek that I am studying. This is the mine drainage output. So the purpose of my experiment was to determine how the addition of mine drainage was impacting rates of decomposition of organic materials, as well as how it was impacting the microbial communities, which are integral in the decomposition of organic materials in the creek beds. And this is two of my site locations. The creek that I'm studying has AMD partway down, so I can compare above where the AMD is to below where the AMD is. So the creek is called Glens Run. We know that this is the AMD input down here. This is a picture I took. So this is halfway down the length of the creek. You can see over here, this is a breakdown of the watersheds in our area. This is all part of the Upper Ohio South watershed. And Glens Run is this little orange one here. And here is an aerial view that just sort of gives you a better idea of what we're looking at. We have a fairly large longwall mining area up here, Tunnel Ridge. We already know that Glens Run has impairments from aluminum, iron, manganese, as well as pH issues. And we have additional stressors from metal toxicity with aluminum, flocculation, sedimentation with iron, and then pH toxicity. This is just a better aerial view so you can see where my locations are. So I've got 5 locations total. I've got 2 above the mine drainage and then 3 below the mine drainage. Everything is equidistant, so 100 meters above the mine drainage input, 10 meters above the mine drainage input, and then we've got the mine drainage 10 meters below, 100 meters below, and I have an outlier here that's about 1,300 meters below the mine drainage down here. And then this is the Ohio River. So you can kind of see up here just a little bit better. They're equally distant apart, and you can just sort of see this red one here is the mine drainage in the middle. That's the input from the tube. So in order to go ahead and run this experiment, one of the main things I did was I created these arrays. So they're pieces of plastic gutter. We've taken PVC tubing and glass slides along with cellulose sponges and wooden veneers. And we've created this enclosure It's got screening over top of it to help keep out insects so that we can determine how much of the breakdown of the materials is due to microbial breakdown as opposed to having, macroinvertebrates breaking down leaf litter and such. And this is just sort of like the process of what I went through to create it. All of the substrates were 2.5 centimeters squared. They're all the same size. And the way that the arrays were placed into the stream was so that this part up here, which is the top, was placed so the flow went straight through the bottom. So all of the substrates were receiving equal amounts of water from the stream where they were sitting. They were adhered to the bottom of the creek bed using rebar and zip ties. They were put out for a total of 6 weeks. At the end of 6 weeks, we went ahead and retrieved them and took them back to the lab. You can see visually, there's already a pretty apparent differences in the breakdown of these cellulose sponges. So this is site 1. This is 100 meters above the mine drainage input. And this is site 5. This is my outlier site, the furthest one away. It is also the one that has the most recovery. So we'll get into a little bit more details, but so just imagine, sites 3 and 4, which are significantly closer to the mine drainage input, and how that affects the decomposition rates. Once I had all of my substrates pulled out of my arrays, and they were all pre-weighed and numbered, I knew which one was in exactly which location in each array. We numbered all of them. We dried them before they went into the creek, and then I weighed them. I wrote down the weight. After the 6 weeks, I took them out. I dried them again. I weighed them again, and then we put them in a muffle furnace and ashed them, which is what these photos are. So this is the remaining result of a cellulose sponge after 6 weeks in the creek, and this is a wooden veneer. And then we did lots of math and stats, which are hard when you're using R. And we came up with some information as far as the breakdown rates of the sponges and the veneers. So this is particularly for the sponges. Your flow is from site 1 down to site 5. The AMD input here, that's 0 meters. That's what we're calling 0. And the way that these box and whisker plots work is this is sort of your average, your normal span of result in how many grams per day we're losing. This line here marks the average total. And then at the end here, we have your outliers. So there could be reasons as to why we have, 1 or 2 that stick out further than the rest of them. But your overall picture shows you that as we get to the mine drainage input, decomposition basically stops for the sponges. It's not 0, but it's pretty close. Site 4 is a bit better. Site 5, again, is really bad. Now, the outlying site, there is a fairly large roadway for our area right there. So there could be some contributing factors as far as to why the decomposition rate drops back down again. I'm still in the process of putting all of that information together. The veneers, you can see, also decrease in their ability to decompose. It's a little bit different. It looks like site 4 has a larger decrease in functionality compared to site 3, which is not what we saw with the sponges. The sponges had a significant impact right at 3, got a little bit better at 4. Site 5, which is the outlier, the box plot is larger, so we have a larger variation happening there, but the overall average decomposition rate is still slower. So I went ahead and put together a site comparison just so you can sort of see a better idea of what the difference in the breakdown is. So for site 1 compared to site 2, site 1 is 0.57 times faster than site 2 for the breakdown in sponges. And it's 0.71 times slower for the rate of veneers. Not particularly sure why at this point. But when you get down to site 1 compared to site 5, site 1 for sponges decomposes 16.5 times faster than the sponges at site 5. And that's pretty impressive. So that's sort of how this is meant to be read. The veneers are being processed slower at site 5 than at site 1. Again, I think that there's going to be some additional information as far as water chemistry and microbial composition that's at play here. But the overall picture is that as you add in the mine drainage, the ability for the stream to break down organic materials is compromised. I also went ahead and took a subset of these substrates from each array, and I used them to isolate bacterial and fungal DNA, which I'm sending out for third-party analysis at this point. I have not had the results sent back yet. I did use the Kaizen DNeasy Power Biofilm Kit, and Zymo will be doing the sequencing. So right now what I can tell you is the DNA that I got out of the stream system is a bit degraded anyway, which is not uncommon when you're dealing with environmental DNA. This is a picture of the gel that I ran. So once I was done isolating all of my DNA, I was able to run a gel just to see if I did have DNA in my samples. You know, was my Power Biofilm Kit successful in isolating any of that information? And the answer is yes. Initially, I was kind of upset because I wasn't happy with the results that I got here. But when I started to really break it down, I realized that some of this lack of DNA is data in and of itself. So over here, I try to make this easier to understand. The purple is the location. So we've got array 1, array 2, which are both above the mine drainage, array 3, array 4, and array 5. The first 3 lanes are sponges. The second 3 lanes are veneers. And then you have sponges and then veneers. And then this first one here on the left side of the green line, that's the ladder. So that's just a way to determine how many base pairs I'm looking at. So what you see really is that for arrays 1 and 2, we do have DNA. It might be degraded, but it's there. Once you get to array 3 and 4, it significantly drops off. I mean, you almost see very little to nothing in most of these lanes, and it doesn't start to pick back up again in any way noticeable until the outlier site, location number 5. So though I'm still waiting for the microbial data to come back with sequencing, so I know exactly what is growing in these different places, the fact that, you know, I can already see that they are being negatively impacted by the mine drainage is pretty interesting. I also went ahead and did water chemistry. So I put the arrays into the creek bed. We did a water grab, which we sent out for third-party analysis through Duquesne, and it was measured for cations and anions, which gives us an idea about like dissolved metals in the water, as well as sulfites, nitrates, phosphates, those kinds of things. And I did weekly water chemistry readings. So every week I went out, I made sure that the arrays were still in the creek bed. I cleared any sort of debris that was on top, or made sure that there wasn't any obstruction to water flow. And then I measured the pH, the temperature, dissolved oxygen, specific conductivity, turbidity, and chloride using the YSI meter. And what I found was specifically conductivity is a problem, which, you know, if you know most anything about mine drainage, you know that that's going to be an issue. So you can see the mine drainage, which I took water readings on as well. The average weekly output for conductivity was 8,709, and sites 3, 4, and 5 are still significantly impacted by that. Whereas you look at sites 1 and 2 and you're at less than 1,000. So that's pretty significant. Temperature didn't fluctuate too badly, even though the mine drainage itself is pretty cold coming out of the hillside. Dissolved oxygen wasn't horribly impacted. pH, we did have a minimal drop in pH. The mine drainage itself is very acidic, but between, you know, with the type of rock we have in the area, I'm not too surprised to see it bounce back up. We have a lot of calcium here. Chloride, there was an increase in that until site 5, and then turbidity. So the amount of turbidity coming out of the mine itself wasn't super bad. There was an increase in sites 3 and 4. Site 5 is very high. I'm going to say that probably has more to do with roadway runoff at this point. The cation and anion analysis, we had a high readings of nitrates and sulfates at the locations. And then the dissolved metals that came back as being problematic were aluminum, manganese, iron, and arsenic. And we already know that aluminum and iron were going to be an issue. Manganese is pretty common as far as mine drainage is concerned, so that wasn't too surprising. I was pretty interested in the arsenic reading though, because my arsenic was actually higher prior to the mine drainage than below the mine drainage. The mine drainage itself did not have very much arsenic in it at all. So I'll come to find out that iron is one of the ways that they, I guess it's oxidized iron, is a way to remediate arsenic. So that would explain why some of my levels below the mine drainage were pretty much nil. But overall, the impact is ongoing. You can see, you know, here's where Glens Run dumps out into the Ohio River. And this is actually pretty minimal. I've had other aerial shots that I wish I had access to right now, where you can really see significant effluent of mine drainage coming into the Ohio. And it's just getting washed downstream. This is obviously a problem through a good portion of the state. So at this point in my experiment, what I can tell you is that the functionality of the stream is significantly decreased. And that is going to be impacted by the microbial communities and the pollutants. So certain fungi are going to be more, aquatic fungi and terrestrial fungi are not, they don't operate the same. And where terrestrial fungi can be very tolerant to certain pollutants, aquatic fungi are more susceptible to metal toxicity. So once I get my results back from my DNA sequencing, I'll have a better idea of what's happening between the microbial communities, specifically the fungi, and the ability for the creek to break down organic matter, which is really important. Freshwater ecosystems are a large part of our ability to break down carbon, sequester it, and then release it back into the atmosphere. And then, you know, additionally, we're having these pollutants that are transferred into additional waterways, and it just becomes a cumulative problem. So that's sort of where I'm at this point. I wish I had a little bit more to offer you. I think that once the microbial information comes back, I will be able to, you know, relate that to the chemistry of the water and the functionality a bit more. But in the meantime, I thank you for joining and for listening to what it was I did have to share. And if you have any questions, I'm happy to answer to the best of my abilities.
Thank you, Katherine. That was great. We've got several questions in the chat for you.
Okay.
Was the microbial composition / breakdown examined within the mine drainage itself?
No. So because the tube is literally coming out of the hillside, there isn't any organic matter in the tube, and the water fluctuates too much to attach an array somehow. There's no way to easily, I guess, monitor how that water specifically is impacting within the tube, if that makes sense.
Yeah, right. right, next question. For breakdown calculations, did you consider the rate to be linear or exponential?
So we did break it down to a linear rate of decay. So it's based on a daily loss over time as opposed to exponential.
Perfect. Is there any data on effects of decomp of any sites that have both AMD and coliform? We unfortunately had a fishbowl in and we're questioning age of decomp with CSO and AMD pollution factors in the watershed.
So we have a lot of fecal coliform issues up here, specifically E. coli, which my lab mate, I think, spoke to you in January about. And one of the problems with having, I guess you wouldn't usually consider this a problem, but having mine drainage that doesn't have a significant drop in pH is that it allows those fecal coliform communities to flourish as well. So you end up with mine drainage that's circumneutral, and then you have, you know, fecal coliform living happily beside it. So I don't know of any papers that have studied, you know, the rate of decomposition, including AMD and fecal coliform. I think it's interesting, and I don't know offhand if it has any impact. But I do know that, you know, our creeks up here do have significant E. coli and fecal coliform issues. So my creek is probably one of those creeks.
Okay, thank you. Just two more. How were the DNA analysis funded?
How is the DNA analysis funded? I have a grant that I received, and I've been able to use some of the grant money through the West Virginia NASA program to pay for it. I am capable of doing it myself in the lab. I have done it before, but at this point, with the additional thesis work I'm doing, it's just easier to have a lab do it for me.
Absolutely. All right, last question. In the 6 weeks when your samples were in the creek, how much did the flows change?
We did not measure water flow on a weekly basis. I will say that the positioning of the arrays in the creek bed, they were never dry. They were set into areas which had consistent flow, but were on the deeper ends of the creek bed so as to prevent any sort of drying out.
Excellent. Well, thank you again so much, Katherine. Gonna turn things back over to Rachel to introduce our third and final speaker for today.
Thanks, Katherine. Great job. Our last presentation, we're going to shine a light on Friends of Deckers Creek, one of our watershed groups located near Morgantown. And they're going to be talking about their AMD remediation projects. So we'll be hearing from Brian Hurley, the executive director.
Hello, thank you so much for giving me this time here. I'm going to see if I can seamlessly share my screen, but I'm not off to a great start. It's funny, before when I kind of did some practice with this, and then I had it, there it is, share screen, got it. And that's what I'm looking for. And share, and okay. Do it live. Okay, all right. And okay, so I'm Brian Hurley from Friends of Deckers Creek, and going to talk to you a little bit about our treatment projects that we have right now. And it doesn't, why is it not? There it is. Okay, I was pushing the wrong button. So I'm Brian, just a brief introduction. So I'm the director at Friends of Deckers Creek. And Friends of Deckers Creek, we primarily talk about abandoned mine lands, or focus on abandoned mine lands. previously, I was a field technician at Friends of the Cheat. And when I was there, I looked at special rec sites, and a little bit more about that and a little bit later. Shaun mentioned that a little bit, so I'm going to mention that a little bit. So hard to believe that I've actually been an operator for 9 years now, which is just really wild for me to wrap my mind around. So you folks know what acid mine drainage is. We talked about the water quality and kind of the parameters that we look for. I know you folks are familiar with this, and so we don't need to talk about that. And so so the biggest offender in the Deckers Creek watershed is the Richard Mine, and right on the right of the screen you can see the white aluminum and the orange iron, and much like Katherine's creek, that's a pretty similar colors. And the biggest dissolved metals we deal with in the watershed are iron and aluminum and manganese. And you can see how many pounds of those dissolved metals we get a year from this particular mine only. So kind of going back to baseline for the water quality, and we like to see 6.5 to 8 pH. And you can see that conductivity and pH changes up and down with the slides. So you folks are all familiar with this, but just kind of set the stage. So here on the left of the screen, we have the Deckers Creek watershed in the light blue, and all of the red items are all the mining around, and most of that is underground mining. And so this one right here, can you see my pointer, or can you not see my pointer? Okay, I don't have that. I haven't clicked on the thing that makes my pointer that cool red laser. But at any rate, so here, this big underground scene, this is the Richard Mine, which is what we saw 1 or 2 slides ago, which is the biggest remaining polluter in the Deckers Creek watershed. So I front loaded a little bit about the abandoned mine land compared to special rec sites. So in brief, Surface Mining Control Reclamation Act was passed in 1977. And so that means any mine that closed before 1977, no one is liable to reclaim it. Any mine that was closed after 1977, the coal mining operators are obligated to reclaim it. I was glad to see in Shaun's presentation that the coal mine operators were indeed reclaiming and treating the water, but that's not always the case. So that's when we have that's where the special rec comes in. So that was special reclamation is a mine closed in 1977 that the mine operator did not clean up the water, and before 1977 is considered abandoned mine lands, and no one is obligated to clean up. So that's where groups like Friends of Deckers Creek step in. So this is some very, very charismatic pictures of acid mine drainage. On the left, we have doing some maintenance on a treatment site, and on the right is just some raw acid mine drainage flowing into the creek. So we kind of have 2 umbrellas of our treatment systems. We got passive sites and we got active sites. And the passive sites are lower cost, lower maintenance. You get effective treatment and you don't have to deal with the power source. I have noticed that I forgot to add this, that their quality of treatment tends to degrade over time as the treatment measures get eroded out. And so then the other umbrella is the active site. And so this we have it's the active site. We need a power source, and you do get consistent treatment over the system's lifespan, but there's a lot more maintenance, a lot more costs, and power source. So those are kind of like just the basics to kind of set the stage. So here is one of the Friends of Deckers Creek passive sites. And the acid mine drainage is collected along this old high wall, goes into that first pond, second pond, third pond, fourth pond, fifth pond, and at the end of that, you're getting good water quality. Notice there's no doser or there's no silo or anything like that. So then we have our active site, one of our active sites. So here we have the water is coming in from right behind this picture here. It's going through the treatment system and into our settling pond. And if you were to open the door there to the silo, you're going to see this particular silo, which is a tipping bucket that delivers a dose of lime to get the treatment system. So that's enough background. And the biggest thing that we want to talk about is this stuff works. On the left of the screen, we've got Deckers Creek 1995. I want to point out the red rocks. Those are all stained by acid mine drainage. And then, I meant on the left. Did I say left? I meant left. 1995 red rocks. And then on the right, we have colored rocks. And this stretch of Deckers Creek is actually quite healthy. It is healthy because of all the work that Friends of Deckers Creek and reclamation groups and people and coal mining operators who do clean up their water quality. So combined, we get our benefit of colored rocks instead of red colored rocks, as well as all the water quality improvements that come with it, which you folks are familiar with. So now to kind of drill into, run low on time here. So to drill into the most recent system, Dillon Creek, this is a passive system that we recently put together. And this is the engineering blueprints. We have the primary seep coming in, the north seep, going into our here is a limestone bed where we're getting our treatment system. And our acid mine drainage treating rather with the pH improvement, and we're settling metals out. So this is the blueprint, and this is the site under construction. We are looking down into where the limestone bed is going to be eventually be built. And after construction, we ended up with this. So this is the completed Dillon Creek treatment system. So this is our north seep collector, our south seep collector. So the water goes in, goes through this limestone bed. It gets its pH improved, and then it is discharged into this artificial wetland, this constructed wetland, into good water quality treatment. So kind of what I really want to talk about here is the things that we had to deal with in order to get this project built, which I think is what, so this is the biggest things that Friends of Deckers Creek face while putting this construction project in. We changed the landowners, and so these are all obstacles that we had to overcome. So change the landowners, but the landowners, so we have everything set up. Then the landowners sold their land, but we didn't have sufficient documentation in the courthouse. So the lesson here is to make sure when you're building a treatment system to put all of your books documented at the courthouse. So if the landowner changes, your permission to enter and build the construction site stays true. The other big delay we had was our permit approval timeline. So this was a grant-funded project, and our grant was a 4-year timeline. But our permit, we had a pretty quick turnaround with our permit approval, but it was still 10 or 12 months. I can't recall specifically. So when you're trying to put a project together, make sure that you have a lot of time for the permitting to go through. Army Corps of Engineers, stormwater permit, historical preservation permit, all the permits. Permit action is we ran into a headache with we had to cut down the trees before March ended in order for us to build for it to be delayed until November because of bats. So we take a really, really long time for the permits to get approved. And then when the permit does approve, we had like 2 weeks to start putting our permit in action. And we were scrambling there, but we got it done. So once again, realistic timelines. The grant, when we wrote the grant, this was 4 or 5 years ago, with very outdated equipment to estimate the cost of AMD treatments. So when you're building a treatment, make sure you add contingency into your budget. So that means the estimated costs over the long time. Make sure you compensate for the increase of pay raises, increase of equipment, increase rates of fuel, all that stuff. The other thing we had was a bit of an ambiguous engineering contract. And this one was the engineer designed the project, but there was no information to actually send out to the contractor. So there was no contracting packet to send out when we're doing our contract bids. So make sure with the engineering contract to have the scope of work outlined specifically. I'll cross all of your T's and dot all of your I's with that. And then we also had project redesigns, which delayed us even further. But the good news is, despite all these, the treatment still worked. This is our system in, 295, system out, pH 6.74. So we're seeing really impressive improvements of the water quality here. And so kind of like the issues that we face were mostly timelines and permitting. But so when you're implementing a project, make sure you plan ahead for those things. I kind of scrambled and raced through that because running low on time, but that's kind of an overview about a few of the parts of building a treatment system.
Wonderful. Thank you so much, Brian. And I'm very impressed you were able to get everything done right by 11. We do have one question for you.
Oh, Becca, I think you're muted.
Are there any? Gosh.
I'm hearing you, Becca.
Okay. Oh no. Can you hear me? Can other people hear me?
Yeah.
I see some nods, so I'm gonna
anyway.
go forward with so, any provisions made for maintenance/renewal of the passive schemes, such as removal of sludge or renewal of limestone?
Okay, so passive schemes. Let's see here. Provisions made for maintenance renewal passive. So we do our best to complete the project while still allowing time for like maintenance and sampling. However, more often than I care to acknowledge, everything gets pushed up against the like end of the grant timeline, and we can't really do the maintenance that is needed. However, the West Virginia DEP has a new branch, maybe in the last few years, where there's a collection of funds to be used to maintenance and upkeep on abandoned mine land site, as well as the bipartisan infrastructure law. They're able to build up maintenance funds for that. So that is part of the so we try to bake in. We want to bake in maintenance. We try to bake in it, but in practice, we often our grant timeline runs out before we can do appropriate maintenance.
Awesome, thank you. And one more question. What is the anticipated longevity of the system?
So the systems, we generate design the system for a lifespan of 15 to 20 years is kind of the standard. Once again, in practicality, it doesn't You get really good treatment when the system is first built, but it's kind of but over the times, like the first five years, you're going to have a significant drop in pH, and then the next 3 years, you're going to have a moderate drop in pH, and then the last few years, the remaining years of the line, the project lifespan, you're barely getting any a pH improvement, and that's just kind of general. Other treatment systems have had different results, but that's seems to be how it pans out.